Hi, I'm Colin. The two main applications of any introductory course on differential calculus is graph sketching and solving optimization problems. In this module, we're going to focus on the former, that is, graph sketching, and apply derivatives to sketch the graph of the cubic polynomial f of x equals 2x cubed minus 9x squared plus 12x minus 3. Alright, so our goal here is to sketch the following cubic polynomial. Have you sketched a cubic polynomial before? If not, you may be feeling a bit stumped on where to begin. If you look back onto the functions that you've sketched in the past, chances are they're usually of a very specific type, most likely linear functions, quadratics, or perhaps one of the basic elementary functions, e to the x, ln x, sin x, or cosine x. And importantly, you sketch those functions using techniques which were quite idiosyncratic, that is, specific to those types of functions. For example, to sketch linear functions, your go-to method might have involved identifying the slope and y-intercept from the equation y equals mx plus b. To sketch quadratics, your go-to method might have involved finding the X-Intercepts, along with deducing whether the parabola was concave up or down, or perhaps using a special formula to find the axis of symmetry of the parabola. And you may have simply memorized what the graphs of the exponential, logarithm, and trigonometric functions look like. But it is important to have robust methods that can be used to sketch the graphs of an arbitrary function, methods that work in general, methods you can rely on no matter what sort of function you're given. As a result, crucial to graph sketching is the concept of finding what's called the turning points of the function. A turning point is either what we call a local maximum or local minimum. To elaborate, we're going to show in this module that for the cubic polynomial we want to sketch, the point 1, 2 is a local maximum. What this means is that this point is higher than all the others around this area. This means that although we have no idea what the overall curve looks like, we do know that locally around this point, the curve must look something like this. Now, we're also going to show that the point 2, 1 is a local minimum. This means the point is lower than all the others around this area. Thus, similar to before, although we don't know what the overall curve looks like, we do have an idea around this point. Moreover, if we knew that there were no other points like this, then barring special features like asymptotes or discontinuities, the curve must look something like this. In fact, this is precisely what the graph of this cubic polynomial looks like. And it turns out that all we needed were the turning points, highlighting how crucial finding local maxima and minima is for general graph sketching. So, how do we find the location of these turning points exactly? The key observation to make is that at a turning point, whether it's a local maximum or minimum, the tangent line is flat. In other words, the tangent line has slope 0. Importantly, this means the derivative must be 0 at a turning point. Therefore, to find turning points, the first step involves finding values of x for which the derivative f-x is equal to 0. So in summary, to sketch the curve for a general function, it's crucial to find its turning points, that is, local maxima and minima. And to help find these turning points, we require the derivative, which explains why calculus is so useful for graph sketching. Finally, besides turning points, other features to look out for are any points of inflection, the x and y intercepts, and asymptotes or discontinuities if they exist. We'll talk more about these later in the module. Alright, having emphasized enough how important turning points are, let us now find them using the first derivative. Differentiating our original function, we get the quadratic 6x squared minus 18x plus 12. It will also be useful to know the second derivative. So differentiating again, we get the linear function 12x minus 18. Note that every time we differentiate a polynomial, its degree goes down by 1. Anyway, to find our turning points, that is, local maxima and minima, we first set the derivative to be 0 and solve for x. Thus here, we get the following quadratic equation. We can then take out 6 as a factor on the left-hand side. Factorizing what's inside the brackets, we get the following. Thus our solutions are x equals 1 and x equals 2. In other words, we have found the x values of our possible turning points. However, we also need to find the corresponding y values if we are to plot them. To do this, we take turns substituting these x values back into the original equation. Thus the y value at x equals 1 is given by 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 minus 3, which turns out to be 2. And the y value at x equals 2 is given by 2 times 2 cubed minus 9 times 2 squared plus 12 times 2 minus 3, which turns out to be 1. Thus, the points 1, 2 and 2, 1 are possible turning points. Now that we've found the points where the derivative is equal to 0, which are called the stationary points of the function, it's time to determine their nature by classifying each of them as either a local maximum, a local minimum, or something else altogether called a horizontal point of inflection. These three are the only possibilities, because only at these sorts of points do we have a flat tangent line. To classify these points, one method we can use is the first derivative sign test, which involves testing whether the derivative is positive or negative around the points we found earlier, thereby telling us how the graph behaves around each point. We first create a little table where we have one row for some x values and another for the derivative. We then write the x values of our possible turning points, which we found earlier to be 1 and 2. And we know that at both these x values, the derivative is 0. We now choose some x values. Firstly, one that's slightly to the left of 1, for instance 0, and then one that's between 1 and 2, for instance 3 on 2, and one more than 2, for instance 3. We then want to test the sign of the derivative at these x values. If you substitute x equals 0 into the derivative, these terms here will vanish, leaving you with just the constant 12, which is a positive number, telling us that at x equals 0, the function is increasing there. In other words, the graph is going up. Similarly, you should verify that x equals 3 on 2, the derivative will be negative, telling us that there the function is decreasing. In other words, the graph is going down. And finally, you should verify that at x equals 3, the derivative will be positive again. That is, the function is increasing once more. What all of this information tells us is the following. Around x equals 1, the graph is first going up, and then plateauing, and then going down. In other words, the graph looks like this. That means it must be a local maximum. Thus we have proven that the point 1, 2 is a local maximum. Now around x equals 2, the graph is going down and then plateauing and then going up. In other words, the graph looks like this. That means it must be a local minimum. Thus we have proven that the point 2, 1 is a local minimum. Another common test for classifying these points is called the second derivative test, which involves checking the sign of the second derivative at each point to tell us whether the graph is concaving up or down there. This will immediately tell us whether or not the point is a local maximum or minimum. Here we want to evaluate the second derivative at the two x values 1 and 2. At x equals 1, the second derivative is 12 times 1 minus 18, which is just negative 6, which is certainly a negative number. This means that at x equals 1, the graph is concave down, which shows that it's a local maximum. And at x equals 2, the second derivative is 12 times 2 minus 18, which this time gives positive 6, which is certainly a positive number. This means at x equals 2, the graph is concave up, which shows that it's a minimum. These results are consistent with what we found with the sign diagram method, which is that we have a maximum at x equals 1 and a minimum at x equals 2. If you're wondering which method to use, the first derivative sign test always works. However, it may be a bit tedious to use at times, especially if the original function is complicated. This means provided the second derivative is easy and quick to find, it may be a better idea to use the second derivative test. Be aware that if the second derivative outputs 0 at any time, then we say that the test fails and you must use the sign diagram instead. Having found the all-important turning points, let's now talk a little bit about concavity and inflection points. Recall that the second derivative tells you about the concavity of the function. Specifically, at this part of the graph, which is concaving downwards, the second derivative would output negative values here. And at this part of the graph, which is concaving upwards, the second derivative would output positive values here. Thus, at this point, where the concavity changes from concave down to concave up, the second derivative will be 0. A point where the concavity changes is called a point of inflection. Thus, the first step to finding any points of inflection is to grab the second derivative of the original function and set it to be 0. Thus here, we get the following linear equation. Now, rearranging for x, we thus get x is equal to 18 on 12, which is just 3 on 2. Therefore, a possible inflection point occurs at x equals 3 on 2. Now, substituting this x value back into the original equation to find the y value, we get the following. Which turns out to also be 3 on 2 here. Hence, the point 3 on 2, 3 on 2 is a possible inflection point. To verify that this is indeed an inflection point, we can employ a sign test very similar to before, but this time testing the second derivative. Now, we know that at x equals 3 on 2, the second derivative is 0. We then choose an x value slightly to the left, for instance 1, and one slightly to the right, for instance 2. We then want to test the sign of the second derivative at these x values. If you substitute x equals 1 into the second derivative, you get 12 minus 18, which is negative 6, which is certainly a negative number, telling us that at x equals 1, the function is concave down. And at x equals 2, the second derivative turns out to be 24 minus 18, which is positive 6, telling us that at x equals 2, the function is now concave up. This shows us that a change in concavity occurs at x equals 3 on 2, from concave down to concave up, verifying indeed that we have a point of inflection there. You may also attempt to find where the curve cuts the x and y axes. To find the y-intercept, you evaluate the original function at x equals 0. Here, that means all the x terms will vanish, leaving you with just the constant term negative 3. Thus, negative 3 is the y-intercept. More generally, the y-intercept of any polynomial will always be its constant term, since all the other terms will vanish when you set x to be 0. Now, to find the x-intercepts, you need to set the y value to be 0. In other words, you set f of x to be 0. This results in the following cubic polynomial equation, which is difficult to solve. Recall from the pre-calculus part of the unit that finding the roots of polynomials of degree 3 or higher is typically much more difficult and laborious than solving linear or quadratic equations, and involves the use of the remainder and factor theorems, along with polynomial long division. Finally, polynomials don't have special features like asymptotes or discontinuities, so we don't really have to worry about them for our example here. To summarize, we first found the turning points, that is, local maxima and minima. Such points serve to pin down the overall shape of the curve, and is a crucial feature of general graph sketching. We also found an inflection point, along with the y-intercept. The x-intercepts were unfortunately a bit too difficult to find here. And finally, polynomials don't have special features like asymptotes and discontinuities, so we didn't have to worry about them here either. Alright, I hope you found that useful. Be sure to check out the module called Curve Sketching Tips for more useful goodies. See you next time.